Section 5.2 is called the unit circle, but really what we're going to do today and for the next few classes is to define our trigonometric functions. All right, so I want to introduce these to you with this graph here. So I want you to imagine this circle that you're looking at is a circular track. It's about 6 miles around, and you are the green dot, and you're going to run around this curve, or walk if you're not a runner. All right, so we're going to go around this curve. And what I've got Desmos doing in red is tracking your mileage. Okay, so you're going counterclockwise around this circle, and the red distance is how far that you've traveled around this track. All right, so I'm going to take us back to the start, and then I'm going to draw a curve off to the right. It's going to start off at the origin. All right, so what this curve is going to do, on the x-axis, it's going to track your distance as a straight line distance. So I'm going to take you around the circle a little bit and show you what's going on. Okay, so here I am at 1 mile. Okay, so you've gone 1 mile around the track, so it's at a 1 tick mark on the x-axis. And what the y-coordinate, what the green line is keeping track of, is how far away you are from the x-axis at any given point. All right, so you're going to see that the y-coordinate on this green curve is following how either high above the x-axis or below the x-axis you are as you run around this circle. All right, so we're going to keep running around the circle or walking. And you see, so when I go below the x-axis, this green curve follows my y-coordinate, and it keeps drawing this curve. All right, so when you use your mileage around the circle to track your x-coordinates and you follow the y-coordinates on the circle, you get what we call the sine function. And you can see this sine function is a very wavy graph. It has tons and tons of applications, anything that's a wave, music, sound waves, light as a wave, any kind of thing that could be modeled by a wave. Sine and cosine, our other trig function, are incredibly important. All right, and they're all based off of a circle, and specifically a circle of radius 1. And I've got that circle kind of scooted over at the center at -2. Normally we look at that centered at the origin. So let's go look at that circle. Okay, so I've moved the unit circle over to its usual spot where it's centered at the origin. It's got that radius of 1. That's why we call it a unit circle. And you can see its equation up there in the upper left-hand corner. X squared plus y squared is equal to 1. That's true for any point around this unit circle. Let's see, and I also have an angle drawn in standard position. All right, every angle that you draw in standard position is going to hit this unit circle somewhere. So no matter where that angle is, positive, negative, big, small, it's going to hit the unit circle somewhere. And the place where an angle hits the unit circle is called its terminal point. Okay, so that green point that I've been dragging around the circle is called a terminal point. And that terminal point is incredibly important. The terminal point is how we define our sine and cosine trigonometric functions. All right, so once you have found that terminal point, the x-coordinate tells you what the cosine of that angle is, and the y-coordinate tells you what the sine of that angle is. So our main goal today is to get coordinates of lots of different angles written down, their terminal points on the unit circle. All right, so posted on Blackboard, I have these blank unit circle pages that we're going to fill out. Our goal is for a bunch of these angles to get their terminal points labeled with their x and y coordinates, because we saw on the last slide that the x and y coordinates were going to give us the cosine of the angle, comma, the sine of the angle. So the only easy angles to come up with the terminal points for are the quadrantal angles. And remember that those are the angles that when we draw them in standard position, we land on an axis. And these are easy to come up with because we can remember that the radius of the unit circle is equal to 1. Okay, so let's pick some quadrantal angles. Let's see, let's do 180 degrees. So if I draw 180 degrees in standard position, I would end up over here. And we know that 180 degrees is also pi radians. So we're going to label degree measurements, radian measurements, and terminal points here on the unit circle. And this point is on a circle of radius 1. It's on the x-axis, so its coordinates are going to be -1, 0. And again, that tells you that the cosine of 180 degrees is equal to -1. The sine of 180 degrees is equal to 0. You could go ask a calculator. It would agree with you on that. Let's see. Now you can see I've got all these spokes around the circle. If I keep drawing this arrow for all of them, it's going to look like a mess in the middle. So we're typically not going to draw that arrow in the middle. We'll just kind of understand that we mean the terminal side of an angle drawn in standard position. Okay, other quadrantal angles. How about halfway to 180 degrees? That would be 90 degrees. That would stop us here on the positive y-axis. That's halfway to pi, so that's pi over 2. And that point's easy too, right? That's on the y-axis, so the x-coordinate is 0, and radius of 1 means a y-coordinate of 1. And now we know the cosine and the sine of 90 degrees. Down at the bottom of the unit circle, let's go down there. Let's see, this would be another 90 degrees from 180, so 270 degrees. We could convert that to radians, or we could just kind of think each quadrant is worth a pi over 2. So 1 pi over 2, 2 pi over 2, 3 pi over 2 lands us down here. And this would be the point 0 in the x direction, -1 in the y direction. And then we got one more quadrantal spot that's over here. And that's going to be the point 1, 0. We could think of that as being 360 degrees. Okay, so a full revolution would be 360 degrees. Pi got us halfway around the circle, so 2 pi would be a full revolution. We also would think about this spot, though, as the angle that is 0 degrees. So that's where you start off on the positive x-axis and you don't go anywhere. Okay, so this is also 0 degrees, which is also 0 radians. So that's the only one we label with 2 different measurements on our unit circle. And so those red, blue, and purple spokes are going to be the angles 30 degrees, 45 degrees, and 60 degrees. Okay, so this red spoke is where I would land with a 30-degree angle. Let's see, our blue spoke is going to be 45 degrees, and then our purple spoke is 60 degrees. All right. So when I convert those into radians, you can multiply those by pi over 180. You get that 60 degrees is pi over 3 radians. 45 degrees is pi over 4 radians. And 30 degrees is pi over 6 radians. And it would be really helpful if you have those conversions, just 30, 45, and 60 degrees converted to radians memorized. When I was learning this, I just kind of remembered that 30 and 60, I swap 3s and 6s when they're going from degrees to radians, and then 45 gets the pi over 4, so it kind of matches up there. And that'll just help as we're converting all these other angles. All right, so pi over 6, the terminal point for pi over 6 is, let's see, root 3 divided by 2, comma 1 divided by 2. Okay, all of the points around the unit circle have kind of ugly coordinates because they're all between 0 and 1, so they're all either fractions or decimals. But they all follow that equation, x squared plus y squared is equal to 1. The terminal point for 60 degrees is actually the reverse of that, the mirror of it. So the terminal point up here is 1/2, comma the square root of 3 over 2. And then pi over 4, the terminal point for pi over 4 is the square root of 2 divided by 2, comma the square root of 2 divided by 2. And it should kind of make sense that at 45 degrees, you get the same x and y coordinate, since you're going down the same number of degrees from the y-axis as you're going up from the x-axis, that you're going to get the same x and y coordinate at that point. All right, so in the next video, we're going to fill out the rest of this unit circle using a little bit of symmetry.